My name is Acharya, and today I'm presenting my project on an adaptive thrust vectoring UAV designed for disaster response in extreme coastal environments. Coastal regions, especially places like Florida, are increasingly exposed to hurricanes, tropical storms, and flash flooding. When these events occur, emergency response depends heavily on rapid aerial assessment for search and rescue, infrastructure inspection, and situational awareness. However, this is exactly when most UAVs fail. High winds, turbulence, debris, and payload variation destabilize conventional drones, limiting their effectiveness when they're needed most. The core engineering problem is that most commercial UAVs are designed around calm, near-linear operating conditions. Severe wind disturbances, nonlinear aerodynamic effects, and changing payloads introduce dynamics that traditional fixed-gain PID controllers struggle to handle. As a result, drones lose hover position, exhibit oscillations, or require expensive hardware upgrades to remain operational. This creates delays in rescue, poor data quality, and increased risk to human responders. To address this, there is a clear need for UAV system that can maintain stability in turbulent environments, adapt to payload variation, collect reliable real-time data, and deploy rapidly in disaster scenarios. Meeting these needs requires not just stronger hardware with more intelligent control. This is where my project creates a blue ocean opportunity. If you look at the current industry landscape, most disaster UAVs compete on hardware strength. Conventional drones are moderately priced but unstable in wind. Military-grade UAVs offer high stability but at extremely high cost, slow deployment, and limited accessibility. The market competes almost entirely on physical robustness, not control intelligence. My project shifts competition away from hardware and towards software-driven resilience. Instead of adding weight, cost, or complexity, I focus on adaptive control intelligence. Using the same airframe, my system achieves significantly improved stability and disturbance rejection through control architecture alone. This creates value innovation, higher stability at lower cost. Using the eliminate, reduce, raise, create framework, this strategy becomes clear. The system eliminates reliance on heavy hardware stabilization and manual retuning between missions. It reduces deployment costs and operator burden, and raises stability, payload adaptability, and reliability in disaster zones. And it creates an adaptive control architecture combining thrust vectoring with fractional order PID control, enabling software-first resilience that scales across platforms. This also opens access to three tiers of non-customers. First, emergency response agencies and NGOs who currently use drones only in calm conditions. Second, disaster teams in small municipalities that avoid UAVs altogether due to unreliability or cost. And third, unexplored users such as coastal communities and infrastructure agencies that currently lack access to resilient aerial systems. This project unlocks users who don't even consider drones viable today. From a technical standpoint, the UAV uses thrust vectoring combined with adaptive fractional order PID control. Unlike classical PID, fractional order control introduces memory effects that allow the controller to balance short-term corrections with long-term stability. Gain scheduling enables the controller to adapt in real time to payload changes when intensity and operating conditions. The result is smoother response, reduced oscillations, and stronger disturbance rejection. This system was developed using a simulation-first approach in MATLAB Simulink, then validated through bench testing and flight testing workflows. The hardware platform is cost-effective and modular, proving that resilience does not require military-grade budgets. In terms of applications, this UAV is well suited for hurricane damage assessment, search and rescue in high winds, flood infrastructure monitoring, and post-disaster mapping. Longer term, this architecture supports autonomous navigation, swarm coordination, and scalable UAV networks for disaster response. From a business perspective, this is not a one-drone solution. The model scales through software licensing, integrating UAV kits for agencies, and fleet deployment with training and support. Because the value lies in control intelligence, the system is hardware agnostic and replicable across platforms. In closing, the UAV market today competes on hardware. My project competes on intelligence. By creating a new market space for affordable, adaptive, disaster-ready UAVs, this work demonstrates how intelligent control design can save time, reduce costs, and ultimately save lives. Thank you.